So we've got a region is defined as the area bounded by, we've got a curve, y equals 4x minus x squared, and we've got a line which is just a curve that happens to be straight, y equals 3. The area is rotated 1 full turn. How else could I say 1 full turn? You have 2 other ways I could say that. 360 degrees or 2 pi radians, yep, okay. Rotated a full turn around the line y equals 3. Find the volume. How have we started every single question so far? A sketch. Right, okay. Y equals 3, I think we all know what that one looks like. Top one here, what's that going to look like? Yeah, I can see Roz doing it in the air. Okay. That top one there, if I'm going to sketch that graph, is it useful to do anything to that equation first of all? Substitute in some key values, that would be good. Anything else? Make it equal 0. Anything else? Factorise it. We'll probably do all of those things. If we factorise it first, what does it factorise to become on the right hand side? And I think it was Ella who already suggested that. Ella. Was it you who suggested factorising it?
Me and Jack.
Oh, you and Jack. Go on, see if you can factorise that for me. Okay, you can just sit at the back for a minute, please. Go on, Ella, what do you get?
X lots of 4 minus x.
X lots of 4 minus x. Yes. Okay. Somebody said put that equal to 0. Put that equal to 0. What do we get from that?
0 or...
Yep. Okay. You said what sort of curve it is, so what we are getting here is a quadratic. I'm going to try and do it in colour if I can. Looking like that. It's supposed to be beautifully symmetric. Well, that's 4, that's 0. Okay. Right, the other line, y equals 3. Well, I know what y equals 3 looks like, but I need to work out really whether it's going above or below just to check. So really, it would be really good to find out what the height is there. How could I find the height there? There's an easy way, there's a complicated way. It's a nice, beautifully drawn, the best ever drawn symmetrical quadratic curve you've ever seen in your lives. How could I find that point there?
When x equals 2.
Yeah, okay, because of the symmetry, okay, of quadratics, that's when x equals 2 here. So when you bung 2 into this, what do you get out when you substitute 2 in? When you substitute 2 in, okay, if you put x as 2 in, you're going to get y equals 4 lots of 2, take away 2 squared, you're going to get y equals 4. So I do know that that maximum point is when y equals 4. So I can now put on the line y equals 3, which is my other line here. Okay, so I've got them relative to each other in roughly the right position. It's not to scale, but at least everything's in vaguely the right place. So I'm interested in the region bounded between the curve in red, the line in green. So I'm interested in this bit here. And it's being rotated around the line y equals 3. We have never had anything yet rotated around a line that isn't the x-axis or the y-axis. Now, if you think back to what we did right at the beginning, what did we say the height of a little strip was? If I, and I don't actually want to draw this on there at the moment, but if I look at that line there, effectively, where the edge of that bit of paper is, what did I say before the height of that line was from the x-axis up to the curve? I just want one very simple answer. The y coordinate, yeah, y. Okay, so that height up to the red one is y. What is the height up to the green line? Where is that green line drawn? Go on. 3. Okay. Now what I'm interested in now is this height here, because this is the bit that I'm rotating. Okay. Then I have, or you guys have just said that that height, that red height, is equal to, say it again, y. That height there, we have said, is equal to 3. So what is this height here that I'm really interested in? The height between the two curves. Y minus 3, yeah. Okay. The entire height there is y. Take off the bottom bit, which is 3. So that height there is y minus 3. So that is the height of my little narrow strip, which we're going to deal with. So, if we're rotating around the x-axis, an x-axis rotation, we had earlier in our red box rule, it was pi y squared dx, because the height was always the y. We're going to adapt that for our scenario that we've got here. What do you think our adaptation will be? Exactly right, yeah. Okay, it will be that. Okay, it'll be that little thin strip. And now what do I need to put on here? It wasn't actually written down on this one here. What is missing on this one over here on the left? It also needs to go on the one on the right. Limits, yeah. So the thing now I have to do is to find the limits. Joe, how would I go about finding limits? Where are the limits? Talk to me in colours of lines or anything. What are the limits? What's it going to be? I'm not looking for numbers or precise answers. I'm just saying, where does that shaded area start and finish?
Like 1, 3, is it?
What?
Like down there.
Here?
Yeah.
That point there?
Yeah.
Yeah, that point there. It's where they intersect. That's all I was looking for. Yeah, where they cross. My lower limit is going to be that value down there. So I'll call that A. My upper limit is going to be this value here, where the lines cross, because that's where the area ends. And I'll call that B. So I need to find my limits, A and B. How? Sam, how will I find those x values, my limits?
Set them equal to each other.
Set what equal to each other? You're going exactly the right lines.
4x minus x squared equal y equals 3.
Yeah, that's exactly right. It's where the red line, the green line are equal to each other. The red line is the equation 4x minus x squared. The green line is y equals 3. Set those equal to each other and solve them. That's spot on. Okay, what sort of thing are we going to get here? Quadratic. Quadratics are nicer when you have positive x squared bits, so I'm going to shift that negative x squared over here. The 4x, because I want to make everything equal to 0, I'll stick that across. It becomes a minus 4x. 3, happy for it to stay where it is. Put it equal to 0. Now I need to find out what those values are going to be. Go on, Roz, you said it?
X minus 3, X minus 2.
Because you factorised. Yeah. Okay, factorise it, solve those, so we get x equals 3 or x equals 1. So, we've got our sum, if you like, our integration over here. We've got the limits. What we need to do is, and why do I always take out the front? Just makes it easier. Yeah, it's a number, it's a multiplier. Take it out the front. Y minus 3 all squared integrating it with respect to x between 1 and 3. Okay, what's the issue we have to overcome now? Yeah, that's right. I got y is over here, but I'm integrating with respect to x. Okay, so first off, it doesn't really matter, I suppose, which way you do it, but what I would do first is multiply out the bracket. Y minus 3 all squared. Jack, what's y minus 3 all squared? Just multiply that bracket out.
Y squared minus 6y plus 9.
Yep. Okay. And as far as the curve is concerned, Sam, as far as the curve's concerned, that red curve we had earlier on, what was y equal to?
4x minus x squared.
Yeah, 4x minus x squared. So that's y squared minus 6y plus 9. So substitute in. Okay, and now we've got rid of the issue that we had a dx at the end, but everything else had y's in there. So there's a dx over there on the right. Now what? Multiply the brackets, yeah. Okay. How would you go about multiplying that out? Just out of interest, how would you do that? Joe's just shaking his head. What does that mean? You wouldn't do it. How would you go about multiplying that out? So I'll tell you how I'd do it. Simple multiplying grid. You've got 4x minus x squared, 4x minus x squared. I would just do it like that, the way you sort of would do something much, much simpler, because the method will still work here as well. Sam, tell me what goes in some boxes.
X power 4.
Where? This one?
Yeah.
Yep. Okay. Joe, tell me what goes somewhere else.
16x squared in top left.
Okay. Other two boxes will be identical to each other. Jack?
4x cubed. No. Yeah. Minus 4x cubed.
Minus 4x cubed, yep. Okay. So that bit there under with the red sort of squiggle is the same as everything that's in red in there. So, next thing to do, multiply it out, write it all out. We've got that I'm going to replace with this, so I've got my 16x squared minus 8x cubed plus x to the power of 4, and keep multiplying out minus 24x plus 6x squared plus 9 dx. We all okay with that? Ross, are you ahead of me? Okay, what did you, when you simplified that, when you grouped those bits together, what did you end up with?
X power 4
Yep,
minus 8x cubed
yep.
plus 24x squared minus 24x plus 9x.
I didn't have the same thing written down, so it might be I've written something down wrong. The x squared bit. 22.
Oh,
Yeah.
sorry.
Okay, that's alright. I just wanted to check, it's quite possible I had that wrong. Okay, right. From there, I'm not going to test your C1 skills at integrating. You can integrate that fine, you can substitute in. I will tell you that from there, just for completeness' sake, when you substitute it in, you get 16/15 pi. And because it's a volume, I would encourage you just to write units cubed at the end. Are we okay with that one? Okay? Right, I have one more for you, which again is slightly different, and then we have covered every sort of scenario that you should see. Okay. Then I've got some real OCR questions. Well, you've got them already. I gave them out last week, which you should be able to work through. Okay. So, final one of these. Jean's paper. Okay. Right. I'll just stop this video clip a minute, actually. Right. Next one. We've got the area between the curves now. This curve is not written as a y equals 1. It's y squared is less than or equal to x, and the other curve is y is greater than or equal to x, and the area between those is rotated 2 pi. What's the symbol for radians? Let's see, 2 pi radians around the x-axis. Find the volume. Which of those is the more challenging one to sketch? Pretty obviously the y squared. Put it equal to x for a minute. How would you go about sketching that? Do you know what it looks like? Do you know what it's related to? What would it be what would be nicer on the left of the equals? Sorry? Somebody say it? What would be nicer on the left of the equal sign? Y. Okay. What have you just done to the left hand side? Yeah, so if we square root, what would I get on the right hand side? Yeah, I'll write it like that for a minute, but yeah. Okay, so it's the same curve as that. What does that curve look like? Do you know?
Like that.
Yeah, if you now technically, if you have that written like that, we think of that as being just that bit. Okay, just the positive bit. But yeah, when we write it with the power of a half, usually we don't just consider that, we consider the plus and the minus bit. So yeah, it will look like that. Okay, y equals x, well we know what that looks like. So, a sketch first of all. Okay, we've got the curve here, which is y squared equals x. We've got the curve, the other curve is y equals x. There's got to be an area between them. It's got to look like that, otherwise you won't have anything between them. So what we're interested in here is this little bit of area here. What are the limits in this question? One of them's obvious from looking at the drawing.
0.
Yep, okay. So that one there is 0. What is this limit here? Where x equals root x. Correct. That one there is where x equals root x. When does x equal root x? When x is 1 and when x is 0, yeah. So that is 1. Okay? So, because of that relationship there, we can find out that that very easily is 1. You could put them equal to, solve an equation, stuff like that, but yeah, that's going to be 1. Okay? Now, what we have got here is the area between two curves. It's not like the last one, which one was a horizontal line. This is two diagonal, well, a curve and a diagonal line. It could be a curve and another curve. We're going to adapt our formula. So the normal formula we've got is pi y squared dx. That is the normal formula we use. But if you are doing it between two curves, you do this. You integrate the top curve's equation squared, take away the bottom curve's equation squared. You still got your pi you still got your dx. Effectively, it's pi first y squared, take away second y squared to give you your overall y squared. So our top curves equation was the green one. The green one was y squared equals x. The bottom one was y equals x. And what we've got here, it's still the y bit that we are doing here. It's still y squared effectively in there. So the top curves equation is y squared equals x. So silly question, but what is y squared equal to? X. Yeah, that is y squared for the top equation. And for the bottom equation, I want to write down y squared. Well, that's what y is equal to. So what's y squared equal to for that equation? X squared. I'm integrating with respect to x. My limits are 0 and 1. So does everybody see how I've used that red box rule thing to get these? So, can you have a go at just finishing that from there, because there's nothing new involved in that now. That's just the integrating bit, okay? For the benefit of those who are watching this on YouTube, and I've frozen it in class. There we go, there's the answer.